If you remove the side panel on a desktop computer, you'll see something like this. Towards the front, you should have a drive bay into which you can mount one or more hard drives. A standard hard drive is 3.5 inches wide. You should also have another somewhat larger bay for CD and DVD drives. CD and DVD drives are standard 5¼ inches wide. At the back of the system, either at the top or at the bottom, you should have a box which is the power supply. The power supply is the component into which you plug the power cord running from the wall socket. Everything else in the system which needs power gets power from the power supply. And a power supply is very necessary because the power which comes directly out of your wall socket is very erratic. The power supply takes that erratic input and converts it to a more regular, consistent power stream at the proper voltages for all the various components. Up here, mounted in the back of the case, is a fan. Cooling in your system is very important because some components malfunction when they start getting too hot. The large circuit board mounted against the other side of the case and into which everything plugs in is called the motherboard, or sometimes called the main board. Here's a closer look at a typical motherboard. Down here in the corner we have all of the connectors which we saw on the back of the system. On the other side we have the connector where we plug in from the power supply, and above it are two IDE connectors, which is a connector used for hard drives and also for CD and DVD drives. IDE is a legacy connection that's being phased out, though I would say still most CD and DVD drives use IDE. The big square thing on the motherboard with all these little holes into which we can insert pins, that's the socket for the CPU, the central processing unit, which we'll talk more about in a little bit. Just notice for now it's surrounded by this black piece of plastic. That's the mount for the heatsink and fan which you put on top of the CPU. A heatsink is just a big piece of metal used to conduct and disperse heat, and you need to put that flush up against your CPU because the CPU generates a lot of heat. And then on top of the heatsink you need a fan which is meant to blow away the hot air. These four long slots next to the CPU socket are called DIMM slots, and this is where you plug in these little module circuit boards that contain RAM chips. RAM stands for Random Access Memory, and it's something we'll discuss a little bit later. Up in the top left corner we have these four SATA or SATA connectors, which is the latest standard for hard drives and also CD and DVD drives. And then over here on the right we have what are called expansion slots. Expansion slots are used for devices that need very, very fast connections, where it's not adequate to use some kind of cable, and so instead the circuit board itself gets connected via these metal contacts which fit into the slots here. These two slots here use the PCI standard. This black slot below uses a newer standard called PCI Express, or sometimes called PCI-X. PCI Express is a much faster kind of connection that was introduced specifically for what are called video cards, which we'll discuss in a moment. First though, here are two kinds of cards which you might plug into the regular PCI slots. A sound card, as the name implies, is an expansion card for adding sound capability for recording and playback. And a network card, unsurprisingly, is for adding a network connection, an Ethernet port. Both of these kinds of expansion cards used to be common, but they're hardly used anymore because on most motherboards you have a sound device and a network device built in. That's why the motherboard we looked at had itself connectors for audio and for Ethernet. Now the motherboard also had a connector for the monitor because the motherboard itself had a video device, something which can send an image to the monitor. So you would assume that computers have no need anymore for video cards in the same way that they really have no need anymore for, say, sound cards or network cards. But this isn't really the case. In fact, many motherboards these days are still made without a video device built in. This is because for certain users, a video card is a far superior video device than the sort of devices that get built into motherboards. First off, today's video cards can control multiple monitors, usually at least two. So as a single user sitting at my desktop computer, I can actually move my mouse between two different screens and have windows on both of those screens, effectively providing me with more screen area. The other big reason to use a video card rather than just use the video device that comes built into your motherboard is that video cards are much better for games. Here, for example, is a screenshot of the sort of game you would want to have a video card for. The scene being rendered here is a complex three-dimensional world being rendered in real time. In fact, a new image has to be generated by the game, hopefully at least 30 times per second, though hopefully more like 60 times per second. And the generation of these images involves a lot of math having to do with geometry, and that requires a lot of computation power. In most programs, the computation, as we'll discuss, is handled entirely by the CPU, the central processing unit. But in the case of games with 3D graphics, a lot of the computation is offloaded to the video card. The video card effectively has a specialized processor for doing these kinds of computations. And so, if you wish to play the latest and greatest computer games, you're going to want the best possible video device. But because a decent video device costs at least $100 to $200, it doesn't make any sense to integrate them into a motherboard, because motherboards themselves rarely cost more than $100. So the video devices which get integrated into motherboards are typically very cheap ones, something which costs at most $5 rather than $200. And whereas these cheap video devices may be perfectly adequate for all the sort of things you do on a computer other than playing games, when it comes time to actually play one of these 3D games, they are really, really terrible. So understand that if you want to play computer games with complicated 3D graphics, be prepared to spend at least $100 for a video card. Earlier in passing, I mentioned RAM, Random Access Memory. RAM chips are pieces of circuitry for storing data, for storing bits. But RAM differs from other kinds of storage. First off, RAM is much faster. It's far faster than, say, your hard drive. Typically faster by a factor of more than 100. So when it comes to just speed, RAM is a far superior kind of storage. On the other hand, RAM is volatile, meaning that when it loses power, all the bits in RAM get randomly flipped. And so when RAM loses power, you effectively lose whatever you have stored there. So this means RAM is not a place where you would store a file, because files are meant to persist even when you turn off the computer. So because of these two properties, RAM is used to store the code and also the transient data of any running program. So for example, when you start a program on your system, it is loaded from files off of, say, a hard drive into memory, into RAM. And then as the program runs, any data created by the program which it needs only for the duration of the program is kept in RAM. Any data which needs to be more permanent has to be written to some non-volatile storage, like say your hard drive. So a compromise is being made here with RAM between speed and volatility. Ideally, RAM would be non-volatile like other storage mediums. But because it is so much faster, we are willing to live with that downside. We also make a trade-off with RAM between speed and capacity, and also speed and cost. Per gigabyte, RAM is much more expensive than other mediums like hard drives. Whereas here in 2010, $100 will buy you about a terabyte of hard drive space, it'll only buy you about 4 gigabytes of RAM. So the typical PC sold today has between 2 and 8 gigabytes of RAM. The CPU, the central processing unit, is the core component of any computer. It's the component which actually executes the program instructions. The CPU is also the component primarily responsible for both reading and writing the data in RAM, and also reading and writing data to the I/O devices. I/O here stands for input-output, and it refers to all the other devices in the system, the hard drives, the video card, the sound device, and so forth. So, in effect, the CPU is really in control of everything else. Ultimately, it is what tells, say, your video device or your sound device what to do, and so it's responsible for what you see on screen and what comes out of your speakers. The CPUs used in PCs today are all part of the x86 family of processors, and they're made by 3 different companies, mostly by Intel, but also by their nearest competitor AMD, and in distant third place, VIA. There are many different actual models of x86 processors, but what makes them all x86 processors is that they understand and can execute the same set of instructions. So a program written to run on an x86 processor should run on any x86 processor, no matter which company makes it.